Hi guys, and welcome to this virtual lecture course on Classical Mechanics and Relativity. I'm Dr. Andrew Mitchell, and in this lecture we'll be discussing relativistic mechanics. That means classical mechanics, but now incorporating the effects of special relativity. In this lecture we'll be drawing quite heavily upon the insights and the formalism that we've developed in the previous part of the course. In particular, we'll be utilizing quite heavily the four-vector formalism that we discussed in the previous lecture. So in the first part of today's lecture, we'll be using the concept of four-momentum conservation. And this will be combined with Einstein's mass-energy equivalence relation, E equals mc squared, and also the fundamental equation of relativistic kinematics that we discussed in the previous lecture. Together, these equations will help us basically solve all of these kind of relativistic kinematics problems that we see in particle physics. We'll be doing lots of examples in this lecture of those kind of reactions. In the second part of the lecture, we'll be discussing the relativistic Lagrangian formulation. We'll see how the principle of least action, together with the principle of relativity, allows us to write down a relativistic Lagrangian. Then we can just go through the usual process that we discussed in the previous part of the lecture course, where we can write down the canonical momentum, conjugate to our generalized variables, and we will see in this relativistic case that this is basically the relativistic 3 momentum. We can also write down the Hamiltonian, which in this case is equal to the total energy, and we'll see E equals mc squared again naturally arise. We can write down Euler-Lagrange's equations of motion. All of this machinery that we developed in the previous part of the course just carries through very naturally. We can do all of the same stuff again, except now we have a slightly modified Lagrangian, which describes the relativistic case. We'll be doing lots of examples in this lecture, and this is basically the culmination of the two halves of this lecture course. We'll be using the formalism that we developed for classical mechanics and the insights from special relativity to discuss in this lecture relativistic mechanics. So let's get down to work.
Before discussing relativistic mechanics in this lecture, let's first recap some of the concepts from special relativity that we'll be using. In particular, we're going to make very heavy use of the four-vector formalism in this lecture. In the previous lecture, we went into quite some detail on four vectors, so if you've not already seen that lecture, I advise you do so now. But this is a short summary. We define a four position, which is a four-dimensional vector living in space-time. This is a contravariant type, x mu, and mu runs over the indices 0, 1, 2, and 3, corresponding respectively to ct, x, y, and z coordinates. We can take a time derivative of this four position to obtain a four velocity, but since the four vectors are objects which transform under the Lorentz transformation, that implies that we need to take the derivative with respect to something that is the same in all reference frames, and that object is the proper time rather than the regular coordinate time, which means different things to different observers in different reference frames. Tau is the so-called proper time. It is the wristwatch time. It is the time showing on the watch of an observer at the origin of their own rest frame. So we can take the proper time derivative of the four position to obtain the four velocity, and we can write that in terms of the coordinate time, d by dt, when we introduce this Lorentz factor gamma here. The Lorentz factor gamma is given by 1 over the square root of 1 minus beta squared, where beta itself is the velocity of the particle in units of the speed of light, v over c. With the four velocity at hand, we can introduce the four momentum. Again, if this is going to be a four vector, we can only multiply it by a relativistic invariant quantity, a Lorentz scalar, as it's called, and that object is the rest mass, m0. So we don't just multiply by the mass of the particle, but the mass of the particle when it's at rest. This is a relativistic invariant because all observers would agree what the mass of a particle would be in its own rest frame. This object is the four momentum, and we'll be talking about that very shortly in this lecture. We can go further and create another four vector, the four acceleration, which is obtained simply by taking another proper time derivative of the four velocity. Again, we can write that in terms of the coordinate time derivative here. Notice that when taking the time derivative of the four velocity in here, we would implicitly have to deal with the time dependence of the Lorentz factor as well. So there we'd have to use product rule and just be careful on that one. Finally, we can define a force, which is the rate of change of momentum as per Newton's second law. But here, of course, we're taking the proper time derivative of the momentum to obtain the force. We can obtain a relativistic version of Newton's second law by noticing that the force is related to the acceleration simply by multiplying the latter by the rest mass m0. Okay, so with those definitions of the various vectors at hand, we can consider some equations of relativistic kinematics, which we're going to be using in the exploration of the mechanics of relativistic problems in this lecture. First of all, let me introduce the relativistic mass. This is taking the rest mass and simply multiplying it by the Lorentz factor gamma. So this gives a mass that depends on the reference frame. Similarly, we can think of the relativistic 3 momentum. That is obtained by simply taking the regular non-relativistic velocity v, multiplying it by the rest mass m0. That object would then be the regular non-relativistic 3 momentum. And when we multiply it by the extra factor gamma, the Lorentz factor, we obtain the relativistic 3 momentum. This is not yet a vector, it's the space-like components of the momentum. We have Einstein's mass-energy relation. This tells us that E is equal to mc squared, but notice here that the m is the relativistic mass, it's gamma m0 c squared. And going further, we have the mass-energy-momentum relation, which connects the energy to the momentum as well as the rest mass. So E squared is equal to p squared c squared plus m0 squared c to the 4. And here notice that p is the scalar quantity, it's simply the magnitude of the relativistic 3 momentum as written here. Using these definitions, we can then write the momentum p mu in terms of the relativistic mass times the speed of light and the relativistic 3 momentum. We can also write this by the mass-energy relation as the energy divided by the speed of light and the relativistic momentum. We'll actually be using these expressions for the momentum quite extensively in this lecture. Finally, we'll be taking a look at the relativistic Lagrangian and looking at the relativistic formulation of Lagrangian mechanics. For a free particle, we derived in an earlier lecture that this takes this form, minus m0 c squared over gamma. Notice that in the non-relativistic limit where v is much, much less than c, this relativistic Lagrangian for the free particle reduces to the kinetic energy, a half m0 v squared, minus m0 c squared. This is a constant. It corresponds to the rest mass energy of the particle. However, this expression for the relativistic Lagrangian obviously goes beyond that, and we can use it also at relativistic speeds. And we'll be exploring that also in this lecture. Okay, so that was a lightning quick recap of some of the things that we're going to need for this lecture. Let's now proceed to discuss relativistic mechanics itself. And the starting point is the idea of the conservation of the relativistic momentum. Let's now consider a system with more than one particle. In any given reference frame, the total energy is conserved and the total momentum is conserved. This implies the overall conservation of the relativistic momentum, which has in its time-like component the total energy divided by the speed of light, and its space-like components the relativistic 3 momentum. Since these components are individually conserved in any given reference frame, then it means that the overall momentum is conserved. But we should bear in mind, of course, that this is the total momentum, which is the sum over all of the constituent particles of our system at any given instant in time. So for any physical process, we have the total initial momentum is equal to the total final momentum. Explicitly here, I am saying that the total momentum is simply the sum over the individual momenta of all of the particles, and this holds at any given moment, both initial and final, for any process. We can also transform the relativistic momentum into a new reference frame by using the Lorentz transformation. So if we have a system described in a particular reference frame in terms of the momentum p nu, then I can convert this to a different reference frame, moving relative to the first with a constant velocity v, using this Lorentz transformation and obtain the corresponding form momentum in the primed reference frame, p mu primed. If you don't know what this notation means, then I suggest you check out the previous lecture on 4 vectors, where all of this is explained. In particular, it's important to understand that energy and momentum are frame dependent. They depend on which reference frame you're in. To convince yourself of this, imagine that we have a particle in free space moving along with a particular velocity. It has a certain momentum, it has a certain kinetic energy due to that velocity. But now imagine we switch to a new reference frame in which we're moving alongside with the particle. This is the co-moving or rest frame of the particle. Here, apparently, the particle is at rest, and it has 0 momentum and 0 kinetic energy. So by this simple thought experiment, we can immediately see that the energy and momentum are themselves frame dependent. In fact, as we perform a Lorentz transformation, the energy and momentum get scrambled up. That's what this equation is basically encoding. So while the energy and the momentum are separately conserved in any physical process in a given reference frame, we can always transform to a different reference frame. There we would still have that energy and momentum are separately conserved, but the meaning of the energy and momentum would be different from our first reference frame. On the other hand, if we compute this Lorentz scalar object here, which is obtained by contracting the contravariant form momentum and the covariant form momentum, then we showed that this is the same in all reference frames. If we perform the Lorentz transformation on both of these two terms to put it into the primed reference frame, we see that this object is the same in both frames, and therefore it's the same in all reference frames. Again, we'll be making use of these facts later on in the lecture. Let's immediately illustrate this concept of the conservation of form momentum by considering the following interesting question. Can a photon, which is a massless particle, disintegrate directly into a massive particle? So this is a kind of classic question one might ask in the realm of particle physics. By Einstein's mass-energy relation, E equals mc squared, one might have thought that we can convert the photon energy, E equals h nu, with nu being the frequency of the photon, into mass of a new particle. But we'll see that the conservation of form momentum actually forbids this. The conservation of form momentum tells us that the total initial form momentum is equal to the total final form momentum. A photon is a massless particle, and as explored in the previous lecture, we have a form momentum that is therefore given by this, where the p here is simply the magnitude of the relativistic 3 momentum, p vector. Together, this object forms the relativistic 4 momentum, p mu, for the initial state. On the other hand, for a massive particle, which we will consider to be our final state of this reaction, we have a relativistic 4 momentum, p mu f, which has an energy, ef, and a relativistic 3 momentum, pf vector. Now, the conservation of form momentum tells us that this initial form momentum has to be equal to this final form momentum. And indeed, we can compare, component by component, these two objects. So in this case, we learn that the initial momentum, pi, must be equal to ef over c, the final energy divided by c. And we learn that the initial and final relativistic 3 momenta must be equal. If the initial and final relativistic 3 momenta are equal, we can simply take the magnitude of that and say that pi is equal to pf, and then we can substitute that into this expression and obtain that pf must be equal to ef over c. To see the importance of this relation, we should now use the fundamental equation of relativistic kinematics. We will do this for the final state, which is supposed to be for the massive particle, and the equation reads ef squared is equal to pf squared c squared plus m naught squared c to the 4. This m naught here is the rest mass of the final state. But since we've just shown that pf is equal to ef over c, we can substitute that in here, and we find that this first term is also equal to ef squared. These two terms on the left and the right cancel, and this tells us that overall, the m naught, the rest mass of the products, must be equal to 0. So indeed, we've proved through using the conservation of form momentum that a photon cannot disintegrate directly into a massive particle. The products of the reaction must be also massless. For a given total energy E, producing mass requires decreasing the momentum, but the momentum is conserved, and the energy is also conserved. Therefore, this reaction is not a possible reaction. On the other hand, as we'll see now, two photons can combine to make a massive particle. Let's consider the initial state of the reactants. Let's say that we have two photons moving in opposite directions. So we have a relativistic 3 momentum P1 for photon number 1, and we'll say that's just given by this vector P here. And then we have the relativistic 3 momentum of photon number 2 here, which we'll say is the opposite, that's minus P. So in the initial state, we have relativistic 4 momenta Pi mu for particles 1 and 2, and they're given by these objects. The total initial 4 momentum is therefore 2p in the time-like component, but the 0 vector in the space-like components. Let's say that after the reaction we have this product, which is a massive particle moving off with some particular 3 momentum pf vector. Its 4 momentum is therefore pf mu, and it has components ef over c and pf vector. Now, since 4 momentum is conserved, we know that pi mu total is equal to pf mu. So we learn that pf is equal to 0, whereas ef over c is not 0, that's equal to 2p. So we again write down the fundamental equation of relativistic kinematics for the products, which is ef squared is equal to pf squared c squared plus m naught squared c to the 4, and again m naught here is the rest mass of the products. By substituting in that pf is equal to 0 and ef over c is 2p, we simply obtain the final result that m naught is equal to 2p over c, which is finite. So indeed, if we have two photons in a head-on collision like this, one with momentum p, one with minus p, then because the overall momentum is equal to 0 in the initial state, we can produce a product with 0 momentum, but the energy of the total system initially is then converted into mass of the final system. The energy of the resultant is 2p over c, related to the momentum of the reactants. Now, you might be a little concerned that this is a very specific kind of reaction in which we have a head-on collision between our two photons here. But actually, this reaction can be viewed in any reference frame, and in particular, the reference frame that we've adopted here is the so-called center of momentum frame. The center of momentum reference frame is the one in which the reactants have a total relativistic 3 momentum, that's the total p vector, which is equal to 0. So I mean that I sum over all the particles j of the pj vector, that should be equal to the 0 vector in the center of momentum reference frame. It's a similar concept to the more familiar center of mass frame from regular classical mechanics. Of course, just because the vector sum of the relativistic 3 vectors is equal to 0 does not mean that the total magnitude of the momenta are equal to 0. And of course, it is this non-zero value here, which enters in the time-like component of our 4 vector, which can be converted into a mass of our product. So the important concept here is that if we have two photons, we can always go to the center of momentum reference frame, and in this frame of reference, we can see that the total 3 momentum vector is equal to 0, and therefore we can create a product that will be at rest in this center of momentum reference frame, and it will have a finite rest mass. By construction, if we only create a single particle as the product of our reaction, and we're viewing it in the center of momentum reference frame, then because of the conservation of momentum, the products must have 0 momentum. And that's of course exactly what we found here. Now, if we start off with a situation that is not already in the center of momentum reference frame, we can always convert to this reference frame using the Lorentz Transformation. And if we wanted to, we could then convert back again afterwards. Let's consider now another instructive example of the decay of a single massive particle into two smaller particles. That's described by this reaction. Big M goes to little m1 plus little m2, and these are of course the rest masses of the particles. We have the usual form momentum conservation, which tells us that the total initial form momentum is equal to the total final form momentum. If we adopt the centre of momentum frame of reference, then that means the single reactant here, the thing with a rest mass of capital M, has a form momentum which has m times c in the time-like component and then 0 in the space-like components. That's because in this frame of reference, the relativistic 3 momentum, p vector, is equal to 0. Basically, the velocity is equal to 0 in this frame of reference. And the mass here is, of course, the rest mass. What about the products? Well, in the final configuration, we have two masses with rest mass m1 and m2, and I'm going to write their 4 vectors in this form. In general, they have a finite momentum, that's p1 and p2 respectively, and a finite energy, e1 and e2. Now, I don't want to write the time-like components of the products in this same form as the reactants. I don't want to write this as m1c and m2c because I'm not going to be in the rest frame of the products. The products have a finite velocity and a finite momentum here, so I'm not going to be in the rest frame. This gives me two equations. I have that mc is equal to e1 over c plus e2 over c, and also that p1 plus p2 vectors are equal to 0. The vector sum of the relativistic 3 momenta for the products is equal to 0. And that's, of course, because we're in the centre of momentum frame, and given that we only have a single reactant, that means that the total initial momenta is equal to 0. The latter tells us that p1 vector is equal to minus p2 vector. Let's just call that p vector now. We'll drop the 1 and 2 labels. But the magnitude is equal, so p1 is equal to p2. Using the fundamental equation of relativistic kinematics and these relations, I now obtain that e1 over c and e2 over c are given by this expression. On the left-hand side, we still have that this is all equal to big M times c. Remember here, big M and little m1 and little m2 are all the rest masses. The difference between the form of the equations on the left-hand side and the right-hand side is precisely because the reactants are at rest and have 0 momentum, whereas the products are moving and have finite momentum p, with the product components 1 and 2 having equal and opposite vector momentum. So what we'd like to know is the momentum p of the products in terms of the initial masses m, m1 and m2. Once we know p, we'll know everything about this system. Therefore, we simply have to solve this equation. It involves the sum of 2 square roots, so we have to do a little bit of algebra to get out the result for p. First of all, I'll take one of these square roots onto the left-hand side, so that I've isolated one square root on the right-hand side, and then I'm simply going to square both sides of the equation. This will get rid of one of the square roots. But you see, when I do that, I still have this remaining square root here, so I play the same game. I'm going to put this onto one side of the equation and square it. So I've moved over this piece to this side and this piece to this side, and before I continue, I can make some cancellations. Here I have a plus p squared, here I have a minus p squared. They can be cancelled, and then I can factorise this piece and this piece with a common factor of c squared. Since then all pieces have a factor of c squared, I can cancel one of the c's with here. That gives me this result, and now I'm going to square everything again to get rid of the final square root. Now I can take this expression and rearrange for p, which is what we wanted to find in this question. And this gives us our final result. So although that might have seemed like a bit of hard work, virtually all of the hard work here was just algebraic manipulations and actually was quite straightforward. The key to the whole thing is simply adopting the centre of momentum reference frame for the whole reaction, then using the form momentum conservation, which we did here, and then utilising the fundamental equation of relativistic kinematics to turn E upon C for the products into these things involving square roots. After that, it was a bit laborious, but it was really plain sailing. And what we end up with is the momentum of the products, and we know how the magnitude is related to these vectored quantities and we know how to convert the momentum and the rest masses into the energies, and so we know everything. The form of this equation is somewhat non-trivial. I don't think you could guess this. You really have to go through this process of using these equations in special relativity. The threshold energy is the minimum energy required for a relativistic reaction to occur. This happens when all of the reaction products have the same velocity, not just the same speed, but also the same direction. Why is this the case? Well, in this scenario, one can find a frame of reference where all of the products are at rest, and hence they would have the minimum kinetic energy, which would be equal to 0 in this frame of reference. The total energy of the products would therefore just be the sum of the rest mass energies, and this is the minimum that it can be. If all of the reaction products have the same velocity, then they can all be simultaneously at rest in this reference frame. So obviously this corresponds to the minimum energy of the products, and therefore, given that energy is conserved, the minimum energy for the entire reaction, and this is the threshold energy. Let's consider another example. Let's do the head-on collision of two massive particles to create a single massive product. So let's consider this following situation. We have two identical masses with equal and opposite initial momenta. That's P1 is equal to minus P2. Let's just call that P vector for the initial situation of the reactants. The magnitudes are the same. P1 is equal to P2 is P. In the final configuration, we have a single massive product with mass m primed and a final relativistic 3-momentum Pf vector, which I've illustrated here. Remember here that, as usual, m and m primed are the rest masses. Now we use 4-momentum conservation. Each of our particles has some mass and some generic non-zero momentum, so we have E1 over C and P for one of the reactants, E2 over C and minus P vector for the second reactant, and then for the products we have some final energy EF over C and some momentum PF vector. So equating these, we find that E1 over C plus E2 over C is EF over C, but also that PF is equal to 0. This is important because it tells us that we are in the rest frame of the products. This was kind of obvious in hindsight because we're in the centre of momentum frame of reference and we only have a single product, so it will be at rest. This scenario will therefore correspond to the threshold energy because the reaction product is at rest and that's the minimum energy that it can have. Because the products are at rest, I can write EF over C simply as the rest mass, m primed, times C. That follows from E equals mc squared in the rest frame. Now we use the fundamental equation of relativistic kinematics for the reactants, which is this equation, and where we notice that Pi we've simply called P, and Mi is simply M. Therefore, E1 over C and E2 over C are the same. They have the same total energy. Plugging it in, it gives me this expression, and then I can take the square of both sides and rearrange to find the momentum. This gives us the final result that P is 1/2 of C into the square root of m prime squared minus 4m squared. This is the momentum of the reactants at the threshold energy, meaning that the products are at rest. The threshold energy itself, from this expression, is clearly just the rest energy of the products, namely m primed c squared. The threshold energy in any other reference frame can be found by simply performing a Lorentz transformation upon this result. So let's now consider some relativistic collisions in particle physics. For example, we'll take the collision of an electron and a positron, which are of course fermionic particles, to produce two bosonic particles, the W plus and W minus bosons. We'll consider this from the perspective of the classical relativistic mechanics of the problem. The rest masses of the electron and positron are equal, let's call them m subscript e, and the rest masses of the W plus and W minus bosons are equal, let's call that m subscript w. Without loss of generality, let's choose our x-axis to be along the line connecting the particles before collision. Here it's the positron and the electron. Furthermore, we'll choose the centre of momentum frame of reference. Later on, we'll consider different frames of reference. For now, let's again consider the centre of momentum frame of reference for the reactants. Now, since the masses of the reactants are equal, this implies that the momenta are equal and opposite for the reactants, and the relativistic energy of the positron and the electron before collision is also equal by symmetry. The four momenta for the electron and positron before the collision are therefore given by these expressions. As I just mentioned, by symmetry, we can make some simplifications, and that gives us these expressions, where now E subscript E is the same for the positron and electron, and P subscript E is equal and opposite in this central momentum frame. There's one other simplification we can make, because we suppose that the line of centres connecting the electron and the positron is along the x-axis. That means that PE is directed along the x-axis. Then we have that the relativistic three-momentum PE vector is simply PE 0, 0. It's all along the x-axis. Likewise, when we write this into our 4 vector, we have simply zeros for the y and z components of the relativistic three-momentum. What about after the collision? Now we have the W plus and W minus bosons, which could be fired out at any arbitrary angle, and we write down that their relativistic 4 momenta, P mu for the W plus and W minus particles, take this form, where I allow for any general energy E W plus and E W minus, and any relativistic 3 momentum P vector W plus and W minus. As usual, we now utilise the conservation of the total 4 momentum before and after the reaction. Using these definitions and comparing element by element, we obtain the following. Comparing the energies, we get that 2E subscript E is the sum of EW plus and EW minus. And then component by component along the x, y, and z directions of the relativistic 3 momentum, we see that W plus and W minus have to be equal and opposite. This applies component by component. All components can actually be finite, providing they sum to 0, which means they're equal and opposite in practice. The final ingredient is the fundamental equation of relativistic kinematics, which we can apply for each particle separately. So if we consider a particle alpha, which can either be the electron or the positron, or the W plus or minus bosons, we can write that E alpha squared is C squared P alpha squared, plus M alpha squared C to the power of 4. So we can apply this to each of the particles. Now let's consider this reaction at the threshold energy. As I mentioned earlier, this is when the products are all at the same velocity, so we can find a frame of reference when they're all simultaneously at rest. Since the initial total 3 momentum and the final total 3 momentum are equal to 0 in the centre of momentum frame, then the minimum energy must arise when the products are themselves at rest. And this means the relativistic 3 momentum for the W plus and W minus particles are not just equal and opposite, but they're individually equal to 0. Since the particles also have the same mass, this tells us from the relativistic kinematic equation that the energies must be equal. Furthermore, since they're at rest, we can equate this to the rest energy, which is simply mW times c squared by Einstein's famous E equals mc squared equation. This energy is therefore the minimum energy for the reaction to occur. It's the threshold energy. All of the kinetic energy of the reactants is used to increase the rest mass of the products. There is no extra energy left over for the kinetic energy of the products. That's why they're at rest at the threshold energy. With this information at hand, we can then go back and work out the momentum of the reactants in a very similar kind of fashion to how we did in the previous examples. As our final example, let's now consider the same reaction but viewed in the rest frame of one of the reactants, rather than in the centre of momentum frame as we considered previously. So let's consider the electron at rest, and then smashing into the electron a positron at great speed. I can then write down the 4 momenta for the positron and the electron as follows. Without loss of generality, I'm again going to consider that the line connecting the 2 reactants is along the x direction. That's just a coordinate choice. In particular, for the electron, we're in its rest frame, and so the momentum is equal to 0. The energy here is therefore the rest energy, and so I can write it in terms of the rest mass, me, times the speed of light, c. After the collision, we have a pair of W bosons, W plus and W minus, and because we lack the symmetry now of the centre of momentum frame, we have to allow for general energies EW plus and EW minus, and general relativistic three momenta PW plus vector and PW minus vector. As usual, and as always, we exploit the four momentum conservation that tells us that the total four momentum before the reaction is equal to the total four momentum after the reaction. Comparing element by element, we obtain the following. We learn that me, the rest mass of the electron, times c squared, plus the initial energy of the positron, is equal to the sum of the energies of the products. We have something a bit different from the centre of momentum frame here, because there is a finite momentum of the reactions in the x direction. So this is actually different from the head-on collision case. In this frame of reference, we cannot have that the products are both simultaneously at rest, because the sum of their momenta along the x direction is finite and set by the momentum of the reactants. This means that either one or other of the W plus and W minus bosons must be moving after the collision. This means that the products have some finite kinetic energy. Not all of the kinetic energy of the reactants can be used to generate the larger rest mass of the products. This simply follows from conservation of momentum. Therefore, in this frame of reference, the threshold energy for the reaction must be higher than simply the rest mass energy of the products. It has to also include the kinetic energy of the products, which has to take away this excess momentum. So what is this threshold or minimum energy for the reaction to occur in this reference frame? As mentioned earlier, the minimum or threshold energy arises when the products have the same velocity. That velocity does not have to be equal to zero, it depends on the reference frame, but the products do have to have the same velocity at the threshold energy. This implies that at the threshold energy, the relativistic free momentum vector Pw plus is equal to Pw minus. Using our general conservation of four momentum expressions here, we can then conclude that the x components of Pw plus and Pw minus are equal, and equal to 1/2 of Pe plus, whereas the y and z components of W plus and W minus are all equal to 0. Now, using as usual the fundamental equation of relativistic kinematics for each particle that I've written down here, together with our energy conservation equation which we derived on the previous slide, as well as our momentum conservation equation, we can then solve the equations to find the initial momentum of the positron Pe plus required at threshold to make this reaction happen. At threshold, this is something that's completely determined by the rest masses of the reactants and the products. Squaring both sides of the equation, we obtain this, and we notice that there's some cancellation we can do. In particular, Pe plus squared, c squared appears on both sides of the equation, and we can also collect up some of these constant terms, as well as dividing by a factor of c squared throughout. Then we get this expression, and again we can square both sides of the equation to get rid of the final square root. That gives this expression, and now finally we can rearrange for Pe plus. After a little bit of algebra, this is the final result. We see, for example, from this square root that the mass of the W particles must be greater than that of the electrons and positrons for this reaction to work. That then means that this square root would be positive, which is what we need for the momentum on the left-hand side. Physically, that's because at the threshold energy here, the products are at rest, and therefore the initial kinetic energy of the reactants is turned into additional mass of the products. I can then plug this result for Pe plus here back into our fundamental equation for relativistic kinematics at the top, and this will give us the energy of the positron at threshold. And that's the result I've given here in blue. Finally, we can write down the threshold energy for this reaction. It's this energy of the positron plus the energy of the electron. The energy of the electron, of course, is just the rest mass energy of the electron because it's at rest in this reference frame. Overall, when you plug that in, you get that the threshold energy is 2 mw squared over me times c squared. Now, we can actually compare that to the threshold energy in the centre of momentum reference frame, and we'd see that it would be different. And of course, it's correct that it should be different, because the threshold energy does depend on the reference frame. In the centre of momentum reference frame, we found that the threshold energy was 2 mw c squared. Here, we find it's 2 mw squared over me c squared. We get something different in different reference frames. Of course, in particle physics, there are many different kind of relativistic collision reactions that one can consider. Here I've just given a couple of examples, but in the end they all boil down to the same kind of processes that I've illustrated here. Hopefully, through this selection of worked examples, you will now be able to go away and do these kind of calculations yourself. In the final part of this lecture, I want to review relativistic Lagrangian mechanics. In the first part of this course on classical mechanics and relativity, we explored classical non-relativistic Lagrangian mechanics in quite some detail. Now I will show how to extend and generalize this to the relativistic world. In fact, we'll see that a lot of the concepts very simply and straightforwardly carry over, and therefore we won't actually need to go into much detail here. We can basically just recycle everything that we did in the first part of the course and use it again here. The first and most important step is to write down the Lagrangian for our system. We have a free piece which corresponds to a single particle with no potential, and as we derived in the previous lectures, that can be given by minus m0 c squared into the square root of 1 minus v squared over c squared. And in the non-relativistic limit, this is basically recovering the usual kinetic energy term. It can also be written in terms of the usual Lorentz factor here, but bear in mind that it does depend on the velocity v of the particle. To find the total Lagrangian, we then subtract off the potential, whatever that might be for the particular system at hand. For example, let's consider a simple harmonic oscillator in 1D, but this time a relativistic version. We have the free piece in one dimension, where the velocity here is now x dot, and then we subtract off the potential, which is a Hooke's law kind of force, 1/2 kx squared. This would correspond, for example, to a mass on the end of a spring, but now we're considering it moving at relativistic velocities. Let's now consider in particular some of the properties of a free relativistic particle in 1D. This is the simplest case we can consider, and we'll build up the complexity shortly. The Lagrangian is of course then just the free Lagrangian in one dimension, which is given by minus m0 c squared multiplied by the square root of 1 minus x dot squared over c squared. X dot here is the regular velocity in coordinate time. It means dx by dt. We can now consider the generalized momentum px, which is conjugate to our generalized coordinate x. As usual, px is given by the partial derivative of our Lagrangian with respect to the velocity, partial dl by dx dot. With this expression for the free Lagrangian, we obtain this expression for the conjugate momentum. This gives us that px is actually gamma m0 x dot, where gamma, as usual, is the Lorentz factor. This is very straightforward to generalize to 3 dimensions, in which case we can write down a vector of our conjugate momenta, consisting of px, py, and pz, and we'd simply find that it was gamma m0 times the velocity of the particle v. This is of course nothing other than the relativistic 3 momentum that we were considering in the first part of this lecture. So the Lagrangian method very quickly generates some of the results that we derived from the 4 vectors earlier. Let's now go back to 1 dimension and consider the Hamiltonian. This, of course, is obtained by Legendre transformation of our Lagrangian, so h is equal to x dot times px minus a Lagrangian L. That gives the following expression for the Hamiltonian. Now we can actually combine these two terms if we standardize the denominator, and we do that by multiplying this second term here by the square root of 1 minus x dot squared over c squared. Then we obtain something like this, and now we can simply add up these two terms. And in fact, we have something nice happen, because this c squared here cancels with that c squared, and then we have m0 times minus x dot squared, and that cancels with this first term. The whole thing then simplifies to gamma times m0 c squared. Since the Hamiltonian gives the total energy E in this system, and given that we have a definition of the relativistic mass, m is equal to gamma m0, in terms of the rest mass m0, we have hence derived the famous Einstein mass-energy equation E equals mc squared. This was a lot easier than the method we applied in the first part of the lecture. We can see that all of this is very powerfully incorporated into the relativistic Lagrangian mechanics framework. So we now know the total energy of a relativistic system. What about the kinetic energy of this system? Well, we can define the total energy at a given velocity as E of v. The non-kinetic piece is therefore the energy E of 0 when the velocity is equal to 0. Everything else is the kinetic energy T. So the total energy is mc squared, whereas the rest energy is m0 c squared. The difference, therefore, is the relativistic kinetic energy that we're interested in. In terms of the Lorentz factor, the kinetic energy is therefore m0 c squared multiplied by gamma minus 1. Notice that for relativistic systems, the relativistic kinetic energy is not simply a half mv squared, as it is in the non-relativistic case. There are relativistic corrections to that formula. However, if we were to take the non-relativistic limit of the velocity much less than the speed of light, then we would indeed find that the kinetic energy recovers the classical result. The last thing that I want to talk about in this lecture is the Euler-Lagrange equation of motion for a relativistic system. We can still formulate this in coordinate time. We don't have to have a manifestly covariant formulation if we don't want. For example, I can write down the action as the time integral over the path of the particle of the Lagrangian, and then the principle of least action tells me that the correct classical path, even including the effects of special relativity, is the one with the minimum action, ds is equal to 0. If we use the usual machinery of variational calculus, we'll be able to derive the equations of motion. And these are, of course, the Euler-Lagrange equations of motion. In fact, nothing in the derivation changes when we consider a relativistic Lagrangian. So the coordinate formulation, which involves the coordinate time t rather than the proper time tau, results in the standard equation of motion. So for generalized coordinates q being the Cartesian coordinates x, y, and z, we have the familiar expression partial dl by dq is equal to d by dt of dl by dq dot. In this expression, we simply use the relativistic Lagrangian, which for a single particle in three-dimensional space, using these generalized coordinates, is minus m0 c squared into the square root of 1 minus x dot squared upon c squared, minus y dot squared upon c squared, minus z dot squared upon c squared. And then from that, we simply subtract the generalized potential, which could in principle be a function of the generalized coordinates, velocities, and also time. Finally, this can be straightforwardly generalized to multiple particles in 3 dimensions. We simply add up all of the Lagrangians for the individual particles labelled j here, and this forms our total Lagrangian. And this is the thing that we then plug in to our Euler-Lagrange equation of motion. We then have 3n generalized coordinates, an x, y, and z coordinate for each of our n particles. Correspondingly, we have 3n Euler-Lagrange equations of motion, which we can then solve. I won't go into more detail on this now. All I want to say is that all of the machinery that we set up in the first part of the course on Lagrangian mechanics can be straightforwardly now applied to the relativistic case. All we have to do is use the relativistic Lagrangian. Everything that we've discussed so far has been in the context of special relativity, and therefore we've been considering flat Minkowski spacetime. This formulation becomes much more complicated in general relativity when we have a curved spacetime, and then we have a more general form of these expressions. However, that's beyond the scope of the current course, so I won't discuss it further here. So, to summarise, in this lecture we used the 4-vector formulation, and in particular the conservation of the 4 momentum, to consider various types of reactions in particle physics. We utilised Einstein's mass-energy relation E equals mc squared, as well as the generalisation, the mass-momentum energy relation. We considered threshold energy, which is the minimum energy to make a reaction happen, and we also considered relativistic Lagrangian mechanics, in particular how we can set up a relativistic Lagrangian and use Euler-Lagrange's equation of motion to do regular mechanics problems, but now incorporating the effects of special relativity. This then brings us full circle to the material we covered in the first part of the course on classical Lagrangian mechanics, but now we've generalised to relativistic speeds. In principle, we could now go back and look at all of the examples that we considered in the first parts of the course and repeat them for the relativistic case. The formulation is exactly the same, we just have a slightly modified Lagrangian. However, the solution of Euler-Lagrange's equations of motion in that case are much more complicated. I will go through some specific examples in a future lecture.